In recent years, there has been a renewed effort to go back to the Moon, this time for its resources, as orange soil samples have been discovered on the Moon. We have been tasked by our client EGB320 to demonstrate a Technology Readiness Level 3 rover, which can collect at least 3 lunar rock samples. The rover needs to collect samples which consist of orange golf balls, both visible and obscured from the moon lander. It is also important that the robot can easily find the samples in the open or recover samples from underneath rocks. These samples would then be transported back to the lander for chemical analysis. From discussion with the client, we have made a list of a few constraints to follow. The rover was not to exceed a CubeSat size of 15 centimeters cubed. It should also collect the samples in 5 minutes or less. It should be less than 1.3 kilograms and is not to exceed a budget of $185. To accomplish these goals, we created a 2-wheeled lunar rover to find samples and return them to the lander.
The sample collection system is integrated into the main chassis of the design for an enclosed and effective system. The sample is aligned with the main collection plate via a state machine utilizing information from the vision system. By interacting with the navigation system, it is able to correctly align and capture any open sample. The gate is used to further confine and control in open samples, preventing unexpected ejection, while also being multi-purpose, allowing the rover to interact and flip rocks to reveal the sample beneath, again using information provided by the vision system.
The vision system takes live inputs from an 8-megapixel Raspberry Pi camera module positioned on the front of the robot. It then converts the data from RGB to HSV, as the HSV's color space allowed for a greater range of light conditions and more reliable readings when compared to RGB. The system then compares the captured frame with HSV threshold values that were calibrated for the environment with a calibration GUI before the demonstration. This comparison results in a frame with distinct objects segmented from one another to be analyzed. The analysis process involves a morphological opening to remove noise and mitigate false positives of objects. The contours of each segmented shape are then found using OpenCV's CV2 library and used to calculate the range and bearing of each object and frame. The range was calculated using similar triangles and the known constant dimensions of each object. Similarly, the bearing was calculated using the relation between the centroid of each contour and the camera module's resolution. Finally, the vision system overlays an outline of these contours with a live video feed, with relevant labels of range and bearing for each object. It also stores each of the labeled objects in frame into appropriate classes to be utilized by the navigation subsystem.
Hi, I'm Drew, and I designed the navigation system for our lunar rover. The navigation system uses an array of information from the vision system to decide which path the robot should traverse. Using a state machine, the robot was able to adapt the navigation planning system depending on whether it was locating a rock or sample, navigating towards a sample, or returning a sample to the lander. The implemented path planning system utilized a combination of reactive and potential fields methods. Potential fields were used to navigate towards the rocks, samples, and lander, while a reactive method was adopted to navigate around obstacles within the scene. This combination approach allowed the robot to navigate effectively, and when combined with a robust mobility system, we navigated throughout the demonstration without fault.
Hi, I'm Jack and I worked on the mobility system. My task for the mobility system was to get the rover moving and to integrate each system with the electronics. The rover uses 2 brush DC motors to move around. These motors were chosen for their high torque and low RPM. This was so that they could maintain the required slow speed of under 5 centimeters per second. Dual direction control is then achieved by using a PWM-controlled H-bridge connected to the 2 motors. Direction and speed control were then programmed using Python. The motor system was then integrated with the rest of the electronics via a 12-volt boost regulator. There was a second buck regulator which supplied the Raspberry Pi and the other electronics components needing 5 volts, like the servos and LEDs.